Andrew, thank you to all of the organizers. I hope to hear, I hope to see my slides. Thanks again. What I'm decided to speak about here is just another model of superfluid helium. Most of the people knows the two-fluid model, so I want to speak about this less known one-fluid model, just to not as an alternative model, but just to a complementary model, as I wrote in the title of this webinar. As you know, just very quick, you know that the helium is a gas helium. When you cool down the temperature very towards the 0 Kelvin, then the behavior change, passing first to the classical liquid helium for temperature below 4 Kelvin, more or less. And when you reach the lambda point, you find the so-called liquid helium. Two different names are used for this transition to superfluid helium. What you realize that below this lambda point, you see that the properties of helium changes. You find what is usually named thermal waves, single sound, or it is able to flow in narrow channels. From these properties, the name is superfluid, and are quantum turbulence, and also the so-called thermal conductivity, which depends on the geometry of the channel, and many other properties which are, of course, probably which makes this system very interesting to study from different point of view, from different approaches. Just to go back in the past, in the last century, there are all the experiments made in a channel where in this channel on the top right, you see that there is a channel with the radius r. If you apply an ether from one side, then what you see that the ether inside can flow inside the channel in a helium bath. And apart from the presence of second sound, which it's quite usual in superfluid helium, you see that the relation between the external applied flux Q, capital Q, which is essentially given as the heat current, the total heat you apply to the channel, is not properly proportional to the gradient of T, but depends on the situation we are considering. If you call L is the mean free path of the heat carriers, you see that these terms, which is essentially the reciprocal of the thermal conductivity, depends on the geometry of the channel. But different behavior appear when for instance, the heat flux grows to either value. As you see in this picture below, when the heat flux is higher than a critical value, the behavior change from the so-called Landau regime to other regimes, which is probably the gradient of T is proportional to Q to 3. Later was discovered that is for the appearance of quantum turbulence there. But also it's interesting, there's called the ballistic regime. So when the mean free path is of the same order of the radius of the channel, the behavior is quite strange or different, because it depends on some terms which are, for instance, F, the fraction of phonons, which undergoes the scattering from the walls, and other velocity of the phonons, the specific heat, and so on. So the behavior change at lower temperature, this is the last one appears, for instance, when you go below to 0.7 or below 1 Kelvin, essentially. As I said, there is a vision, there is the two-fluid division, most of you probably knows, which is due by this Landau, the last in the 40 in the 40 years of the last century, which sees essentially that the superfluid is made by two components, one normal and superfluid components. Each one has own velocity, density. Each one has own properties. The first one, for instance, a classical viscous fluid, which means that the velocity of the normal component satisfy the Navier-Stokes-like equation, for instance, or the superfluid component still being in viscid fluid has satisfy Eulerian-like equation. Of course, it's quite difficult. To my knowledge, I don't know, but I haven't seen before that you are not able to separate the two components. So in some sense, is a kind of model which allows to describe the existence of the properties of helium. The contour velocity, as said, the experiment I considered in the previous slide may be explained by the two fluid description, because you see that the heat is transported carried by the normal component and which counterflow by the superfluid component. So this means that the net mass flow is zero in across the channel. And this is the main idea, what you see in terms of the two-fluid model. Of course, as I said before, when the applied heat is higher than a critical value, it is classically explained by the presence of the quantized vortices. So this means that for Q higher than a critical value, you see that the filaments of vortex lines appear, which are particular kind of vortex, which fixed core. The singularity is based on the superfluid component, and you have a vorticity, but the main properties of these vortices is the circulation of the superfluid component around it is fixed, the quantized. For this reason, the name of quantized vortices. When the turbulence increases, it is expected that the length of these vortex filaments grows, and for this reason you can define vortex line density L, is an amount which is the length in a small volume inside the channel. With this is a classical approach. So in this term, the relation between the gradient of T and the Q in those experiments may be explained. This part of the experiments may be explained by the presence of the L, which is the vortex line density, which grows when the external applied heat flow grows. Let me change the idea which was the basic idea of the last century, which is not probably applied, not only applied to superfluid, but is a general situation, which can apply to a different situation or different physical system. For instance, nanosystem. There is very strong debate on these arguments. It was a strong debate in the last century, because this is a simple example show you that in the left side you consider, for instance, the balance energy equation, which is essentially given the energy density epsilon and the heat flow outside a sample or a volume lambda. No, this part may be zero if you don't have source of energy inside, and we consider the Fourier law in the left side. It's a classical mathematical problem. So if you assume that epsilon depends on the temperature, only on the temperature, you arrive to the parabolic equation. It's a kind of equation which is the temperature, the variation of temperature in time is proportional to Laplacian square of T. And if you consider a kind of bar, simply like a bar in one dimension, you assume that the temperature is one at x equals 0, you find that the solution is the ones you see here, is just the parabolic solution. And there is the paradox of infinite speed of propagation, which means that it's not possible that you have an infinite propagation of heat of temperature, especially in those systems where you reveal the presence of thermal waves. So there was my Maxwell and Cattaneo model, which is the simplest model you can consider, where you have to consider for the flux, not probably given by the Fourier law, but you have a kind of relaxation time for the heat flux. It depends on, this means that the Q depends on the time. And following the same situation, the same calculation, you arrive to the telegraphic equation, which is an hyperbolic equation, which whose solution is kind of temperature. You have a kind of wave temperature, so with a velocity, which is given, the velocity of the wave is given, is proportional to the thermal conductivity lambda, but is inversely proportional to the relaxation time, which works as important tool for the propagation of thermal waves. So this is the basic idea to which most of the researchers in the last century argued on the presence on the constitutive equation for heat flux. So probably for the heat flux, you need a balance equation, and you need to consider it not in some system, of course. You need to consider it inside the variables, the mean variables of the system, instead of consider it as a constitutive equation for it as a core for in the Fourier law. Just to give an idea, clearly the arguments are very important, but I want to give you just an idea how it works, the so-called extended thermodynamics. Of course, classically, the thermodynamics consider mass, momentum, others variables as main variables for your system. But when you are out of the equilibrium, you need, as we see in the previous slide, you need to consider other variables. One of them may be the fluxes of the main variables, as the case for the heat flux. So in the standard thermodynamics, you need to consider the right variables. So where are the classical variables together with the fluxes, but those fluxes which for whom the constitutive equation are not valid. This means that the variables are enlarged. You have more variables, and you consider a kind of general balance equation for them, where V is the variable, JV is the flux of the variables, and sigma is just a source term, which may be positive or negative, depending on the contribution of inside the small variable. All of this equation has to satisfy the equation which you may consider for the entropy, because the entropy, especially the production of entropy, sigma S, this one has to clearly, when you have the evolution of your system, because you are out of equilibrium, the second law has hold. This means that the production of entropy has to be positive, positive. Let me remark that here the entropy has to depend on all the variables, which means on the V variables, which means that not only on the mass, momentum, energy, and so on, but also on the heat flux. For instance, if we required on the fluxes of higher order, this means that from this point of view, this model allows to be dynamics in the sense that in your model you may consider much more variables as you need, just to the idea. So what is the main idea of this of the extended thermodynamics allows to write some equation for the superfluid, because here we have the mass balance equation, which is a classical we have also in the two-fluid model. The momentum balance equation, where B is the mean vehicle. We are not speaking about the two-fluid model, but just a fluid. The energy balance equation, and also the heat flux equation. In red, you see the presence of what essentially we may consider in the Fourier law, no, the classical Fourier law. The lambda is the thermal conductivity, tau is the relaxation time, and so we have the appearance of other terms. Q dot is clearly the material derivative, and other terms which the flux of it. This term is the flux of the heat flux. So of course, in extended thermodynamics, you need the flux of the main variables. And from applying the procedure so on, we of course, it's quite heavy to explain, but just to give an idea, we arrive to this expression for these two are the non-equilibrium stress tensor, and lambda zero is lambda zero is the bulk density. The bulk viscosity, and eta is instead the shear viscosity, and the divergence of V and Q are of course the velocity heat flux, as entropy, the temperature. So this is the main one of the simplest model. I want to stress that two things. The first one is that the flux, for instance, the flux of heat flux has this constitutive equation, but for this one, maybe have, if required, an evolution equation for it, so that in principle, you can build a hierarchy of equation which make the model much more complicated than the one I show here. And furthermore, the other thing is that the sigma q is the production term. The production term means in this expression is given by simply this term, which is because of the Fourier law, but different kind of sigma q may be considered. And in this slide, for instance, if I consider this is the equation of heat flux, here we have the thermal the production of the heat flux, and in principle we can have in the absence of vortices we have the terms which led to the which in some sense allow the appearance of the Fourier law inside the equation of heat flux, no? These terms together, these terms. But if you consider the presence of quantized vortices, which in this model are at the moment are external entities which interact with the heat flux. So here we can consider, for instance, this term, which is the classical term proposed by John Wienen. Essentially, who is familiar with the two-fluid model recognizes in this term the mutual friction force in the presence of rotating system, or this term, which is essentially the mutual friction force in the presence is proportional. It's proportional to the mutual friction force you have in the counterflow experiment. Or in general, you may consider an integral over in a volume where different vortices are considered. S prime is the tangent vector you have for a vortex line along a vortex line. So in this kind, you need to consider the product vector with respect to the field it flux. And you can make much more complicated systems. I want to stress again that here the one fluid model may works at the mesoscopic level and at macroscopic level. We don't have practically the problem you of course have in the two fluid model, and where you have considered of course the mesoscopic situation or the macroscopic situation, because of course the presence of vortices. Let's make just a strong, very quite quite easy comparison between the two models. The two models works in different. The viewpoint is quite different, but both of them describe quite well some behaviors you see in helium. Just we recognize that both models has a further degree of freedom. So in the two fluid model, what Landau thought is just when you go down the lambda point temperature, the superfluid has a further degree of freedom, which is the appearance of the superfluid component in some sense. On the other side, you have the appearance of the heat flux Q when you go down the lambda temperature or lambda temperature, but of course you may have further fluxes of higher order. So in this sense, the approach is quite different. So the first one may be just make, if you want to give a title, an aerodynamic approach. The other one is a thermodynamic approach. So the approach is different, but the idea may be one complementary to the other one. So following this idea that we can enlarge the variable for your system, you can combine, as you know that the field L may change in time, but may change also because of is not homogeneous in the system. So in some sense, you may consider a further equation for the vortical lines. And you can use the extended thermodynamics to consider the equation for this system. And in this sense, you make the you apply the tools of the thermodynamics, the extended thermodynamics there. What you see is that when you apply thermodynamics, appear new fields, because here now L is a main field, no? It becomes to the main field of your system. What happens here that in the equation of heat flux appear the gradient of L, and below we have the variation of L, in dot means the derivative with respect to the time. You have the flux of flux of L, which is proportionally, this model is proportional to the applied heat flux, and there's a further term which is the source terms for the vortical lines. And this here we can consider what proposed by John Winen with the classical Winen equation, no? This which is proportional with this term, which contribute to the growth of the lines, vortical lines, and the other one to the destroy of the vortical lines. But of course, you can here add whatever you like as production term for the vortical lines. And I want to show just this situation that if we in the first one, for instance, the first equation, we are in the condition where Q dot is practically zero, no? Maybe it was neglected because it's practically zero. We can, from the first equation, we can find the Q as proportional not only to the gradient of T, but also for the gradient of L. In particular, I think when you have an heater and you switch off the heater. So in some sense, you switch the gradient of T somehow. There may be a situation where the gradient of T can be removed from this expression. So when the gradient of T is practically zero, you have an heat flux due to the gradient of L, which is so in some sense, if you have a tangle of vortices which is not homogeneously distributed inside the channel, so you have that a gradient of L may lead to the appearance of heat flux Q. So if you, it becomes much clearer to us if you substitute this term in the second equation and you arrive to this expression. Apart from the last two terms, the first two terms, in particular the red one, allow us to see that there is a kind of diffusion terms. Diffusion terms because these two terms are essentially a parabolic equation. So it's a parabolic equation led to diffusions instead of the propagation. There are some results I haven't reported here, but in some situations you may have waves of vortex lines density L. So, but the time is not too much, so I tried to give some hint about this result. And let me go on. Another. I want to now move to try to explain what is found by the experiments, the so-called FT thermal conductivity, namely the FT thermal conductivity, which depends on the geometry. We saw, as you remember at the beginning, we saw three regimes: the Landau regimes, Korte-Melling regimes, namely turbulence, and the other, the ballistic regime. So they can be explained by using the one fluid model in a very simple way. So let's consider the equation. The first equation is the density equation, which leads to the divergence of V equals 0. The third equation, the equation of energy, the equation of energy in the steady state lead to the divergence of Q is 0. The momentum of equation, the equation of heat flux led to these two equations, and this is the simplified form of this equation. And let's consider this very easy cylinder with the heater on one side. Let's consider the cylindrical coordinate here. The heat flux is towards x side, x axis. So the gradient P and gradient T depends only on the axis. I want to stress that since the local thermal conductivity, which is a local amount, is suspected to be quite high, we can drop down this term, which we recognize the London expression here. The problem of the boundary condition. The problem of the boundary condition, that's 2 points, is a problem we have also in other systems, in a solid nanosystem, for instance. But here we have chosen that the V is 0 on the wall, the field, the V. For Q, we have that is 0 when the mean free path of the heat carriers is very small compared to the radius of the channel. Otherwise, it's different from 0. Let's move to the other slide just to show how can we solve it. It's quite easy to integrate. It's a classical, sorry, let me go back a little bit just to say that I write this equation, the second equation, in terms of the cylindrical coordinate, and I find this expression here. These two conditions are because we are in the Landau regime, which means that the mean free path is small compared to R. So Q on the wall is 0, and we arrive to this expression here, which is exactly what we expect to find in the experiments. So the gradient of T in the absence of vortices, we can say, of course, we are in the absence of vortices. We are able to find the proportionality between the gradient of T and Q. So in some sense, we have the macroscopically because we have integrated over the channel, across the channel. We have integrated across the channel. So these are macroscopically expression which relate the gradient of T and the external applied flux to our tube. Of course, the thermal conductivity here is not constant, but it depends not only on the temperature, but also on the radius of the channel and the geometry itself of the system. If you change, of course, the geometry of the channel, it will change accordingly. It depends, of course, it will depend on, of course, on the integration we have here. Ballistic regime, again, following the same procedure here, the solution is the same, but what we changed the boundary condition. So essentially what we have done here is the boundary condition is not zero for the flux on the wall, but we have brought this expression from the microfluidics. We arrive to this expression for the relation between the external flux, heat flow, Q, capital Q, and the gradient temperature. In the case of air is quite small to the mean free path of L, we arrive to this expression, which is the exact expression found in the experiments with the made below 0.7 Kelvin by Grewal. And the expression can be found very easily if you define that the eta is equal to this expression where L, I repeat, is the mean free path of heat carriers, the phonon practically, the velocity of the phonon, the density of the normal component, and here in the R2. Of course, we can have also an expression for in the case of turbulent regime, which lead to the expression of the Korteweg-Melling. Here we can also have as the expression for, of course, in this case, we need to take into account the equation for the vortical lines density with a different expression for the production time. This slide is just to show you very quickly. So I go on just to show you that. Let me pass to the other one just to show you that we are this model is also able to describe the Korteweg-Melling regime because, of course, as I told you, the presence of L explain the Korteweg-Melling. But of course, in this situation, we find the same explanation by using a classical approach of the two-fluid model. So this slide was just to have a panoramic vision that using the one-fluid model, we are able to describe all the three situations we made in the experiments, namely a Landau regime, which means the mean free path is small compared to the radius of the channel, and in the absence of quantized vortices. The situation in the ballistic regime, so which happens for when the mean free path of the system is comparable to the side of the channel of the system you are considering, which happens not only for temperature below 1 Kelvin, more or less, but also for system whose dimension is closer to the mean free path of heat carriers. I speak about heat carriers, but of course it may be also phonon or rotons. The last two strange behaviors. If we speak in terms of strange behavior, if you consider the one fluid model, and we try to study, as we usually do in the two fluid model, we try to study the perturbation of small amplitudes of the mean variables of your system, which in the two fluid models are the normal component and the superfluid component in terms of velocity, density, and so on. In our system are density, temperature, velocity, and flux. And we start, it's a classical approach. We study, we consider the steady state solution, which is given by density constant, temperature constant, velocity zero, and heat flux zero, steady state without anything which is moving. A small perturbation you bar, and you try to consider a small perturbation. When you assume that cap is given by the real and complex part, and you define the velocity as given by omega over KR, which is the real part, you arrive to find in superfluid, in the one fluid, using the one fluid model, you arrive to explain the presence of the fifth sound, which is the classical sound, which is given by the variation of the pressure with respect to the density, and the second sound, which is thermal waves, and which is proportional to this Greek zeta, which is lambda over tau, where lambda, I want to remind that lambda is the thermal conductivity and tau is the relaxation time of the flux. There you recover the attenuation of this wave of these perturbations. In the first one is for the first sound, the second one is the second sound. This is a very interesting situation occur when you consider the transversal modes. When you consider the transversal modes, we find two very interesting modes, which are the first one we have defined as UN, the second one we define US. Essentially, these two modes are essentially related to the classical two-fluid model, because the first mode particularly is the one, that mode that carried the entropy and the viscosity of the superfluid helium. The other one instead is the opposite, like happens in the two-fluid model. And it's quite interesting that when you find V and Q in terms of UN and US, and you substitute in the one fluid model equations, you arrive to this expression for the normal component for UN and US. Essentially quite similar to the classical usual two fluid model, which I reported the last two equations. The difference between I want to stress that when you recover these equations, you need to remove, or you need to neglect some terms. Neglect some terms. If you neglect these terms, which are essentially nonlinear terms, you arrive to this expression. So just to let you know that are more terms may be considered in this two equation, the first two equation. But in this simpler expression, we recognize that instead of having Vn, as in the two-fluid model, we have the V, which is the mean velocity, and it is allowed for the one-fluid model. It is allowed a component for the S is the entropy, no? S with S is essentially the entropy of the superfluid component. So in this extended model, two-fluid extended model, it's possible to have a kind of entropy carried by this superfluid extended mode. So let's there is another interesting situation we want to let you know, which I want to let you know, that is this one, the problem of the boundary condition. If you think in terms of from the hydrodynamic point of view, namely in terms of the fluid model, it's quite clear, no? The normal component is viscous fluid, so on the wall is zero. The other side, the other one is different from zero. If I follow this approach, this means that V on the wall is practically V on the wall is practically zero. V on the wall should be proportional to US, and Q on the wall should be proportional with sign minus sign to US. If I change the approach, if we change the division, namely, I start from the one fluid model, V on the wall should be zero, I don't know. I can choose a Q on the wall zero. If in the first choice, this would lead to, namely, if V on the wall is zero, Q on the wall is different from zero, this would mean that UN is proportional to S. We are speaking about the value of UN, US on the wall. Instead, the other approach, the other choice, Q on the wall zero, would mean that UN, US should be equal on the wall. There's a different vision of the problem would lead to that probably, if you think in terms of the two-fluid model, starting from the one-fluid model, probably the normal component cannot be zero on the wall. It's an open question. Clearly, I can't give you an answer. We made an experiment. We made a numerical experiment in a channel, two-dimensional channel with Luca Cavantucci in a two-dimensional channel. We have considered vortex points in the channel, in two-dimensional channel, in a counterflow situation. The red ones are essentially vortex points rotating counterclockwise. The black one are rotating clockwise. So there are half of them are positive, the other one are negative. The initial condition for the vortex points are randomly distributed in the channel. This is the steady state at the end of our numerical simulation. What we have measured here is essentially with red the profile of the superfluid component, and with the blue one, the profile of the normal component. We have solved in 2 dimensions the two-fluid model. In the figure, on the top, we have considered the usual two-fluid model. In the other one, instead, we have considered the standard two-fluid model. And what is the difference between them is essentially the presence of V, mind you, the presence of V instead of Vn. So the results are practically equal, so not quite different. We have used the temperature of 1.7 Kelvin, so the presence of a normal component is quite important with respect to the superfluid component. So it is expected that these results, that the two results are quite similar. We have made another experiment. This one, where we have considered this is the classical experiment for the usual two-fluid model. So we have not changed nothing. We have changing nothing in the first in the top. What we change in the below is just the slip. We have allowed the slip condition for the normal component. As you see here, there is a slip condition for the normal component is allowed. This is a value, we have a small value of a slip condition, and another experiment which I show you the next slide here is a higher value for the slip condition. And what we saw is that when the sleep condition, when you allow to the normal component to sleep on the wall, the profile of the normal component becomes flattened. So probably it may be, we don't know. This is an experiment, numerical experiment. We don't know. But if you think in terms of the one fluid model, since we don't know exactly the value of Q on V on the walls, this can be reflected on UN US in the normal superfluid component, in the extended normal and the extended superfluid component, which in some sense maybe have different value, different from zero, maybe different from zero on the walls. And so this is, we don't know exactly. We want to stress, but the way we want to stress that the green line instead in both experiments is the profile of the field UNS. The profile of UNS is in green, you know, in both experiments, and is quite flattened. UNS, I will remind you that is proportional to the heat flux. As shown in this slide, let me go back just to show that UNS, is proportional to the heat flux. So that green line is exactly somehow proportional to the heat flux, and somehow is the profile of the heat flux in both experiments we considered. So let's move to the conclusion. I guess the time is over, more or less. So my idea is just to give you another approach of superfluid helium, which we believe it's important for understand this interesting physical problem, because there are some questions which may be considered, which may be handled by the two-fluid approach. Other ones, there are others which may be considered using the one-fluid model. The situation of heat transport, for instance, we think that it's best maybe understand better when you consider the one-fluid model. Other situations which are closely related to the hydrodynamics may be considered, may be handled by the two-fluid approach. Of course, there are many open questions. We claim that the turbulence, the presence of turbulence in the one-fluid model is unclear. We have considered an interaction between the heat flux with these entities, which knows as quantized vortices. But of course, we don't know if there is another kind of turbulence for the heat flux itself, which is a field here, or other question, which is we believe are we claim that are very important to consider, is the boundary condition for the heat flux and the normal component. In conclusion, here just some reference. I want to stress this. I want to let you know that about this book is coming, is forthcoming. Practically is in press. Just have the cover of this book. So that's all. Thank you for attention.
Thank you very much, Michele. So, does anyone have any questions? If you do, please either raise your hand in Zoom, or if you're not able to speak, please then just pop the question in the chat and I can ask the question for you.
Mm-hmm. So, there are questions, so I can.
I'm not sure.
So,
Yeah, I think there's a question by Niels. Sorry if your hand's been up for a while, Niels.
Oh, let's just put it up. So let me be controversial, right? Because why not? Once you introduce the telegraph type equation for the heat flux, is it not the case that you are dynamically introducing two wave components? So in fact, this is a two-fluid model. So there should be a one-to-one correspondence between this and the usual Landau model. Isn't that the case?
Sorry, do you mean here?
Well, once you put the relaxation time in the heat flux equation, like the heat moves as waves, right? So now you have two wave equation, one for the fluid, or one fluid and one for the heat. So there are two components. It's known that this equation, the telegraph equation, has a second sound. So is it not the case that the model you're writing down is actually, for all intents and purposes, a two-fluid model, and there should be a one-to-one correspondence between anything that people do in the Landau type two-fluid model and your model?
So you mean about the heat flux, no? So
no, the general model you're working with is a two-component model, right? You got
yes.
And so it's a two, and if you think of the heat as a fluid, which you kind of do when you say there is a wave equation for the heat, which you do in the telegraph equation, then you have a two-fluid model.
Yes.
Yes. Why did you call it a one-fluid model?
Yes, you are right. You are right. Essentially this for this reason I made in the title a complementary model, because the idea is essentially that the one fluid model is not another model which are not both models are one is exact right, the other one is wrong. No. What is the idea? Is essentially you can have two different vision, and you can use the both vision depending on what you need. So you are right, because there you are more there in the two fluid model, you have a two fluid, classical speaking, in terms of a viscous fluid Vn and a superfluid component with its own velocity and so on. And you can use the approach of the hydrodynamic approach. The other one, you have the velocity V and the heat flux Q, two fluid. Okay, it's a kind of strong words to say two fluids, but you are right. For this reason, I wrote here in, let me go here. Have a look here, just the last two dots. Both models need to consider a fourth degree of freedom. The first one, the fluid model, is you need to consider to fluid. No, so when you go down to the lambda temperature, another fluid has to appear, the so-called superfluid component. Okay, and the vorticity quantum turbulence zone is related to this field, to Vs, no, to the non-superfluid component. On the other side, when you go back to the lambda temperature, what you recognize that the heat flux field appears. So you are right. A question, open question. In some sense, I brought there. Can you consider turbulence for the field Q? Should be a kind of no vorticity, but the Q vorticity, it vorticity, you can speak about on vortices, but not vortices, Q vortices. I don't know. This is an open question which I can't explain and can't say any. But
thank you. So I agree completely with what you said now, and I think the in your model, when you build the extended thermodynamics, the way I see it is you're introducing more degrees, you more sort of divergences and gradients and so on. So your model is richer, and it is an interesting question, how many of these things how these things map over to the standard two-fluid model. But in principle, it should be a map between the two. And I think you're asking good questions. So thank you for that.
Thank you. So another thing we can say relating this one, for instance, just to follow the observation. For instance, in the two-fluid model, for instance, you have a different situation, the so-called the counterflow, co-flow, for instance. No, is a classical topic there. Essentially, you speak about in terms of the two-fluid model. Co-flow means that both components flow in the same direction. No. If you think terms on the counterflow, this means that the two components flow in the opposite direction. No? The second one counterflow in the opposite direction with respect to the first one. I think it's easier, for me, this is the case, it's easier to think in terms of the one-fluid model. Why? And it can make suggestion, can contribute to the debate about the kind of turbulence in superfluid helium. Because in terms of the one-fluid model, co-flow means that the velocity v is different from zero and the heat flux q is equal to zero. The one is zero, the other one is different from zero. In counterflow experiments is exactly the opposite. Namely, v equals zero and q is not zero proper. V is probably zero and q is different from zero. If you think in terms of this approach, what I realize, thinking in terms of the one-fluid model, that for instance, in co-flow, this means that q is approximately zero, would mean that the degree of freedom of your system is not given by, it's a strong word, no? Rho v q, but is given by rho and v. So this means that behavior, what is expected is the behavior in co-flow of quantum turbulence and so on is quite similar to a classical fluid, because the system, due to in those experiments where the heat flux is practically zero, because, I don't know, you use a bell or something to pump helium in a channel or something else, and in such a way, and you made the exact experiment where the heat flux is practically zero, the degree of freedom you lose the degree of freedom of heat flux, and the behavior of helium should be quite closer to a classical fluid. This is what I expect to, just to consideration.
Thanks, Michele. Are there any further questions?
I don't see there are other questions.